All right, good morning, everyone. Let me just maximize our screen. And I think we left off here. We finished Anaximander, and now we have his student, Anaximenes. We had Thales, and student was Anaximander, and now we have the third person of the Miletus school, this school of thought. Will come down to us from history. Of course, there were many other people who studied with these folks, but these are the people that kind of stand out, introducing new ideas that have come down. And here's an important one that Anaximenes contributes to us. He visualizes the universe with the stars as a crystal sphere around us, completely surrounding us, with the stars on this sphere. So instead of getting just what we see, which is kind of a dome, in a semicircle dome, semisphere dome, he envisions the Earth somehow or other in the center of this enormous sphere where the fixed stars are planted and can turn. Very, very powerful idea, an idea that really stays with us. It's kind of the heart of the model of astronomy, right down to the time of Copernicus. This geocentric model of the Earth being in the center of the universe. Remember, there's always, 2 steps forward, 3 steps back, or 3 steps forward and 2 steps back. Anaximenes also believed in a flat Earth. Anaximenes also needed the Earth to be supported by something. Remember, Thales had water as the fundamental principle substance, and the Earth floated on the water. Anaximander was more abstract. He just needed the infinite or the unbounded or this mysterious substance which could not only support the Earth kind of suspended, but also created all the other substances that we see by different shapes or different densities or different motions. We don't know exactly what he had in mind, but there was this fundamental substance which was more abstract. Here with Anaximenes, we go backwards a little bit. We go back to air, and air is his fundamental substance, and the flat Earth is floating on the air. But what's important is that the Earth is suspended. Well, maybe not suspended. It's supported. Got to be supported by something in his mind, but it's supported in the center of the universe, where the rest of the universe, this global crystal sphere of the fixed stars completely surrounds the Earth. So a very, very, very powerful idea from Anaximenes. We move forward now to another school, undoubtedly the most important school of thought, group of people who contributed so much to our understanding of the universe, and that's the Pythagoreans, starting with Pythagoras himself. We really don't know how to distinguish between the thinkings of Pythagoras and his school, the Pythagoreans. They lasted about 200 years in the Greek world. They were teachers, they were mathematicians, philosophers. They were kind of a brotherhood, almost kind of a religious sect. They moved around from time to time. They were persecuted by other people because of some of their religious beliefs, but their influence on Western thought is very profound, as I think you'll see. We have a number of slides that have devoted to the ideas of the Pythagoreans. So let's start with Pythagoras himself. He goes back, really thought that maybe as a very young man, he met Thales and Anaximander and people like that, and learned from them. He is a figure that is very, very important in our Western culture. As you can see, here's a picture of Pythagoras, a sculpture of Pythagoras on the Cathedral of Chartres. As you might know, that beautiful cathedral has all kinds of sculptures all over it of all the great figures of history in terms of their history, and Pythagoras certainly was one of them. Probably the most important single thing that we can say about Pythagoras and Pythagoreans is that they introduced a level of mathematics to the understanding of the universe, which really is unprecedented before them, and it continues on to this day. This view that the world the universe is built on mathematical principles, and the way to understand the universe is through those mathematical principles, to that the math actually creates the very fundamental understanding, the very fundamental principles which the universe is built on. This is the idea of the Pythagoreans, and it is a profound one, which you say is really the foundation of all modern science, and it continues with us to this day. And we'll see a little bit about what I mean by their thought. Famous story of Pythagoras. He's walking along one day, and take your pick of what the story is. He hears some different hammers being hit on an anvil, hammers of different sizes and different weights, and he notices that they make different notes. Or a bunch of different bells of different sizes and maybe different metals hitting the different bells will make different notes. Or cups of water of different heights of the water, or strings of different lengths, of different tensions being held there by the different weights of the stones, or the flutes, putting your hands on different holes of different lengths along the flute length. All those different physical, mathematical differences creates different notes. Okay, so the idea of sound, something which was never analyzed before in this way, is seen to be created by these mathematical numbers. The different numbers are associated with the different notes. More so, even further, Pythagoras says that notice that the harmonious sounds, the sounds that we find pleasing together, are actually sounds that are created by harmonious numbers, numbers which are in simple whole number ratios. And the dissonant sounds, sounds which don't sound pretty to us, are created by different numbers which don't have simple mathematical relationships. So this is his first example to show that here our idea of not only the creation of sound, but what we feel is beautiful, what we think, what we hear, what we experience as something beautiful as opposed to dissonance, is created by the actual mathematical relationships that underlie the creation of those sounds. So in asking that question, where does this beauty come from? Where does the harmony come from? And his answer is, it is actually in the mathematical relationships. The simple mathematical relationships give us something beautiful and harmonious. Okay? The complex mathematical relationships give us something which is dissonance. And so the bottom line for Pythagoras and the Pythagoreans is that the universe is built on mathematical principles. And if you want to understand the universe and explain it, then you have to go and study those principles and find the mathematical harmony which underlies all of reality. In sum, all of the cosmos is governed, in fact, brought into existence by simple mathematical relationships. Now, this, of course, is very extreme in terms of the mathematics actually is reality. But I don't know, when you go ahead and study modern quantum theory and you find that everything kind of just disappears out of your hands and reality seems to float away and all we're left with are the equations, then you wonder just exactly how profound this Pythagorean idea is, that all that is left to explain reality, after all is said and done, is our mathematics, because quantum theory really makes no common sense, but yet the mathematics can make very accurate predictions of what we measure, but we can't put together some kind of a common sense view of what's going on. All we have left to explain, to describe, is that mathematics. They are, in a sense, the inventors of mathematics as we understand it. I'll just give you an example. They like to play with numbers for no good reason, just for fun, just to study patterns because they thought it was interesting. They had the idea of triangular numbers coming from laying stones down in triangular patterns. So we have the first triangular number would be 1. The second triangular number, putting the next row down, would be 1 plus 2 is 3. 6 would be the next triangular number of 1 plus 2 plus 3, adding another layer of stones down below, a fourth layer would give us 10, the next triangular number, 15, the next triangular number. But they looked more. They said, do you notice that the second triangular number, 3, is equal to 2 times 3 over 2? True, 6 over 2 is 3. But more so, the third triangular number is 3 times 4 over 2. True, 12 over 2 is 6. And the fourth triangular number is 4 times 5 over 2. Yeah. And in fact, the nth triangular number, any number as we go on with these triangular numbers, the nth one is n times n plus 1 over 2. And these are the patterns what they studied and found these things very, very interesting. Clearly, there's no engineering use for this kind of mathematics. This comes from a different place. This comes from just studying mathematics just for its pure beauty, for its pure interest. Well, you look at a formula like that, a general formula, we can generalize from the first 5 triangular numbers. I could ask you, what's the sum of the first 100 numbers? Well, according to the formula, it will be 100 times 101 over 2. That would be the sum of the first 100 numbers, something I wouldn't want to have to do sitting with the calculator, adding all those numbers one at a time. But 100 times 101 over 2, well, 100 over 2 is 50. That would give me 50 times 101, which is 5,050. Yeah, the sum of the first 100 numbers is 5,050, not because I added them up with the calculator, but because I see this pattern and I can generalize the pattern to any number that I like. This is this is modern mathematics as we know it. Here we have square numbers, clearly using squares, square arrays of pebbles. But they go further and they say, did you ever notice that the square number, the second square number 4, is actually the sum of the first 2 triangular numbers? You can kind of draw that line. There's the top is the first triangular number, and the bottom below the line is the second triangular number. And this continues. Okay? Here, the third square number is, there's that on the top is the second triangular number, and the bottom is the third triangular number. And so on. The fourth square number, 4 squared 16, is the third triangular number plus the fourth triangle, and so on. And so we get another pattern, a relationship between the square numbers and the triangular numbers. We find that the nth square number, which is nothing more than n squared, is the sum of the n minus 1 triangular number plus the nth triangular number. Okay? This is what mathematics is. This is what we understand mathematics to be. Okay? And they are the inventors of abstract mathematics as we know it. By the way, this is when you, as an undergraduate math major, if you're lucky enough to have room in your schedule to take number theory, not everybody has room to take that elective course, but if you take a course in number theory, this is generally how the course starts. The course starts by looking at the Pythagorean figurative numbers, and just for fun, just kind of being some warm-ups before they get into the real story of number theory. But this is just what an undergraduate math major would see in the first day of the theory of number theory course. So they are the inventors, really, of abstract mathematics as we know it. They're the ones who solidify the idea that mathematics can only proceed by mathematical deduction, okay? Not by just empirical means, but one had to find proofs for their mathematical statements. They studied mathematics, both number patterns and geometric patterns, purely for their beauty and for their interest. They really had no practical, as a society that they were not engineers, they were not people who, worked with navigation or map making or anything like that. This was purely an intellectual pursuit that the Pythagoreans had. One more before we go. Here we have this other kind of figure of these kind of L numbers. Numbers are in the form of an L, 1, and then 3 is in the form of an L, and then 5 is a longer L. But you notice that 1 is equal to, 1 squared, so that's the first square number. But look at the second square number, which is 4. 4 is 1 plus 3, right? And what is 9? Well, 9 is 1 plus 3 plus 5. Here's 9, a 3 by 3 square. It's 1 plus 3 plus 5. And 16 and so on. 16 is 1 plus 3 plus 5 plus 7. 16, here's a 4 by 4 square. Well, it's equal to 1 plus 3 more stones plus 5 more stones plus 7 more stones. And 25 is 1 plus 3 plus 5 plus 7 plus 9, a 5 by 5 square, and so on. And in general, the sum of the first n odd numbers is equal to n squared. We see this empirically. We see this in this nice visualization. Now you want to go ahead and prove this as a mathematician, but these are the kind of patterns that the Pythagoreans played with and investigated, and really in the process invented abstract mathematics as we understand it today. But we're more interested in their cosmology, and they made great contributions, as we'll see, to the idea of how the universe is structured. It is with the Pythagoreans that we finally get the idea that the Earth is a sphere. They are on no uncertain terms that the Earth clearly is round, it is a sphere, and we'll take a look at their arguments in a movement. All the heavenly bodies are spheres, although they look like disks in the sky. They realize that if the Earth is a sphere, then if you had spheres in the sky, what would they look like? They would look like disks, okay? And so, no, don't be fooled when you look at the moon and the sun. Those are spheres, just like the Earth, okay? And the planets, well, the planets must also be spheres, okay? They just projected this from the shape of the Earth. And they give us this very interesting cosmology here. Let's go through this. Following Anaximenes, they do believe that the Earth, that the universe, is in a crystal sphere surrounding us, where all the fixed stars are on that sphere, and beyond that is kind of nothingness, just the infinite envelope of fire and air and whatever. They really did not know what was beyond that sphere of the fixed stars. But inside that sphere contained the rest of the universe as we understand it. And what was in this, at the center, was not the Earth, was not the sun, but something that they called the central fire. The central fire there in red here. This was the center of the universe, and everything revolved around the central fire. Here is the Earth going around, and we have the moon, and the sun, and the planets, Mercury, Venus, Mars, Jupiter, Saturn, and finally the outer sphere of the fixed stars. So this is their vision of the universe, with the Earth in motion. Yes, the Earth here is in motion. There's one other object, there's one other celestial body, and that's the counter-Earth. It's on the other side of the central fire to the Earth. And so all together, we have the central fire, we have the Earth, the moon, the sun. Let's count these objects. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, counting the fixed stars. Around the central fire, you have, without the counter-Earth, just 9 central bodies. Let's do it again. The Earth, moon, sun, Mercury, Venus, Mars, Jupiter, Saturn, and the fixed stars. That's 9. Well, that was not a happy situation for the Pythagoreans, because 9 was nothing particularly special about the number 9. But the number 10 did have a very important and mystical meaning. And so it seemed appropriate for the Pythagoreans that there should be 10 bodies going around the central fire. And so they simply invented the counter-Earth. Well, we don't see the counter-Earth. They've got that covered. We'll take a look at that in a minute. Okay, so here is another view of the Pythagorean universe with the central fire in the center, and here is the Earth. Here we have the counter-Earth on the same side. It's not clear from the writings whether the counter-Earth was like this or the counter-Earth was over here on the other side. You'll see for a moment it really doesn't make any difference empirically, because we don't see the center counter-Earth, and we don't see the central fire. Well, how can these things be in the universe and not see them? Well, okay. So we'll see the explanation that they come up with. Taking it in order, the sun glows by absorbing the light of the central fire. Okay? The sun does not have light of its own, but it picks up the light coming from the central fire, and it is what we see in the light of the sun. The moon shines by the reflected light of the sun, which is interesting. Instead of picking up the direct light from the central fire, they pick it up from the sun, which of course is correct. Uh, and lunar eclipses are caused by the shadow of the earth blocking the light of the sun coming onto the moon. Okay? This is a very important discovery and a very important astronomical fact, which is true and finally clarified and codified by the Pythagoreans. And you can see where this works out very well. The moon here is closer than the sun, and so the moon can get in the way of the Earth, and we can have the shadow of the. I'm sorry, the Earth here can get around in front and block the sun, so that the light coming onto the moon would be blocked, and we would have a lunar eclipse. Right, the Earth could come around here and block the light to the moon. The Earth revolves each day around the central fire. Yeah, the Earth is in motion here. And when Copernicus comes to try to justify his great new model, where the sun in the center and the earth in motion, he goes back to the writings of the Pythagoreans. See, I'm not the first person who thought of this. Look at the writings of the Pythagoreans. They had a notion of the earth being in motion. So not such a radical idea is what Copernicus tried to argue 2,000 years later. And finally, we get to this idea of why don't we see the central fire and the counter Earth? Well, it's because the Earth also, as it goes around the central fire, the Earth is always, the inhabited part of the Earth is always facing outside. We never see inside. We never see the counter Earth, which is on the other side of us. We never see the central fire, which is on the other side of us. As we go around the central fire, we're always looking out. And that's why we see this, the sun and the moon and the planets and the stars. Well, that's all very nice, very convenient of then why we would never get a view of the counter Earth and the central fire. But notice what it does. No, I'm sorry. The orbits of the sun and the moon and the planets are all bigger than the orbit of the Earth, and therefore that's why they look like they go around us. Because in a sense they're just going around the central fire, but they have a larger orbit, and so they're also kind of going around us as well. And that's why we get that view. Let me go back. But if you're going around, if the Earth is always facing out as it makes this circle, okay, think about it, guys. If the Earth is always facing out as we go around each day around the central fire, the Earth must be rotating on its axis. The Earth must be turning, because when the Earth is here, we're looking out this way. When the Earth is here, we have to be looking out this way. Well, if the Earth was not turning, we would be looking here in. So the Earth is always turning as it goes around. As it's revolving, it must be rotating, so we're always facing out. And that's why we never see the counter Earth, which is on the other side. There are no inhabitants on that side of the Earth. Why? Because they would be burnt up by the central fire. Okay? We're too close to the central fire. So we live out here somewhere. This is their view of the cosmos. Not much of it is correct, yes, of course, but it is quite remarkable that that the Pythagoreans set the Earth not only revolving on its axis, but also moving around some other body. Okay. This need for the counter Earth, where does this come from? It comes from their mathematics. Their mathematics dictates this. Okay, 10 was one of the perfect numbers to the Pythagoreans because it symbolized the universe. The triangular number 10 is the sum of 1 plus 2 plus 3 plus 4. Okay? Well, each of those numbers symbolized one of the elements of the universe. 1 was for the points, 2 was for lines, 3 was for surfaces, and 4 were volumes. This was the mathematics which could create all of the physical objects of the universe, okay, through combinations of points, lines, surfaces, and volumes. Yeah, I know this sounds pretty crazy, this kind of numerology, but this is how they thought of the physical universe as being built up from these mathematical principles, these mathematical objects. Well, that's why the triangle number 10 was a perfect number, was an important number, because it was the sum of all the things which the universe is made up of. And they even had a symbol for it, the symbol down below, the tetraxis comes, I'm not sure if I'm pronouncing that correctly, but this was the symbol of the entire cosmos because it combined all the elements that made up the cosmos mathematically. And so this is why they needed a 10th element going around the central fire. And so the counter-earth was invented to make the math right. It was very convenient. You couldn't see it, so you couldn't disprove it, but it made the mathematics correct, and that was important to them, that harmony dictated that there should be 10 objects going around the central fire because of this creation. And just another view, if I didn't make it clear why the Earth would have to be rotating. Okay? So here's the nighttime. We live here on the outside. We never see the central fire. We never see, here the counter-earth is on the other side. Different artists will put it in different places because we're not really quite sure where it was. We know we never see it. We know it's always, outside of us. But here is the night. Here we're looking out to the night sky. We don't see the sun. The sun is over here. And here, when we come around the other side, well, now this is the daytime. We do see the sun. But again, we only live on this half of the Earth. We don't see the side. We never see the central fire. We never see the counter-Earth. But I think you can see that as we go around here, we're going to have to rotate. We're going to have to turn this face little by little, always facing away from the central fire. So by the time we catch up with the sun, we're facing in a different direction. The Earth has to be rotating on its axis to produce this kind of an idea. So a very modern idea of a rotating and revolving Earth embedded in this kind of crazy numerical model based upon the central fire and the counter-Earth. The counter-Earth kind of lost, and the central fire lost its credence as the Greek world got wider and wider, as it went all the way out to the Pillars of Hercules, out to the Gibraltar and a little bit beyond, and all the way out to the Indus River and to the Indian civilization. As the Earth got wider and wider in this time of its known Earth, we realized, well, shouldn't at some point we should be seeing the central fire? Shouldn't we be feeling that heat as we get around the Earth a bit more? And we're not. So this idea of the central fire and the counter-Earth just couldn't hold up as more and more of the Earth was discovered as we moved on in history. So here, an explanation again of the rotation of the Earth on its axis to stay away from seeing the central fire and the counter-Earth. Other famous Pythagoreans, before we leave the school itself, is Empedocles is very famous for it. He's the one who seems to have introduced the idea of the four fundamental substances of the ancient world: earth, air, fire, and water, and that everything is composed of some different combinations of these fundamental elements. So Thales just had one fundamental element, water, and Anaximenes just had one fundamental element, air, and everything could be created from that one fundamental element. Empedocles gives a bit more elbow room here. He says, no, there are actually four fundamental elements: earth, air, fire, and water. Two of them I've got from the Melita school. We'll add air and fire, and the combination of all of those creates the world that we see it, the physical world that we see it. And this idea of these fundamental elements is picked up by Plato and Aristotle, and then becomes the thinking of the Western world for 2,000 years. It really stays like this until we begin to get people like Lavoisier and Dalton bringing in the modern atomic theory in the beginning of the 19th century. He also held that the sun is twice as far away as the moon. Again, we're beginning to see these quantitative statements. There's no proof of these things is really not even much of an argument. But the fact that they're trying to make these quantitative statements, how big is the sun compared to the moon, are things that we don't see before the Greeks, trying to just speculate about quantities, mathematical properties of things in the universe. He also has a very interesting contribution that light is not transmitted instantaneously, but actually takes a finite amount of time to get from one place to the other. We don't know exactly where this comes from, well, why he would be saying this, but this is clearly in his teachings, and it is, not held for a long, long time, not held until it is actually proven by the scientific revolution, finally demonstrates that this is correct in the 1600s. Aristotle in his writings completely discredits this. This is an absolutely crazy idea that clearly light just, fills the universe instantaneously and travels instantaneously, etc. The other Pythagorean I wanted to mention, we'll take a break here, is Philolaus. He's the one who we attribute this central fire cosmology to. He's the one who kind of built this kind of picture for us. Apparently, Pythagoras himself believed that the Earth was at the center of the universe. It was only his brotherhood, as they moved on in history, began to tinker with it and develop this more elaborate cosmology with the central fire in the center. Also, it is Philolaus that seems the one who coined the word cosmos. And that's the idea that the universe is not just this bunch of stuff, but the universe is pulled together, hung together, constructed together using these mathematical harmonious principles. And the word that would describe that harmony, that integrity of the universe as kind of a one thing based upon the principles of mathematics was this word cosmos. And that's where we get that word from. Okay. I'll take a break here, and before we go into Pythagorean's arguments for the round Earth, any questions so far? Okay, let me continue.
So, Pete,
yes.
I was wondering if this mathematical these concepts are being offered by people from Greece, and so I'm wondering what's happening in other parts of the world, like India. Isn't there some? Um, when does the mathematics of India or the mathematics of the stargazers in the Aztec civilizations? How does how can you put it all together in a unified theory of the cosmos from all of these different great thinkers from around the world?
That's a very, very good question. And as you know, a very profound question. You would have to start reading. You would have to start reading the kind of stuff that I've been reading my whole life, trying to understand this stuff. This is a vast, vast story. Remember, our focus is rather narrow. Our focus is staying here in the Western world. So yes, the Indian civilization makes an incredible contribution through the Arab Muslim civilization of bringing the number system of 0, 1, 2, 3, 4, 5 and place value. That's their great contribution to Western society. That's allowed us to have a modern number system. Okay, they had their own astronomy, they had their own mathematics, a different quality to it than the Greek mathematics. This is an enormous story that we have obviously no time for if we're going to get to the geometric models of Ptolemy and how the Greeks saw the world, and therefore what had to be overturned by Copernicus. So your question is profound, it is enormous, and I just invite you to begin Googling those questions, and you can just get lost forever reading about it.
Maybe that will be your a course you might offer at the end of this semester.
Okay, that's certainly a very interesting idea. But let us continue. The Pythagoreans give us the round Earth. Okay, you know the silly idea that the Europeans of time of Columbus thought the Earth was flat, and he was this bold person who thought that the only person who thought that the Earth was round. Such a silly idea. The Greeks, of course, knew that the Earth was round. Every educated person since the time of the Pythagoreans knew that the Earth was round. And here are the three reasons that they give. We know this, by the way, from the writings of Aristotle. Aristotle was great to explain previous thinkers. He would explain their ideas and then disagree with them. He would say, well, this is why all these ideas are wrong, and here are my ideas. But he's invaluable in teaching us, telling us how previous philosophers taught, because he would go ahead and explain. He would take a few pages and explain their basic ideas. And it's from the writings of Aristotle that we know these three evidences that the Pythagoreans gave. He says, this is the evidence that the Pythagoreans gave that the Earth was round. And of course, he completely agreed with it. Aristotle, agreed with the arguments that the Earth was round. The first one, we all know from standing on a beach and watching a ship go away from us, it'll just sink into the water. Okay. Clearly one very simple argument. Or if you're watching a ship coming towards you, it'll get higher and higher. First of all, you see the smokestack, and then you'll finally see the whole ship. Clearly, you're looking at a round curve of the horizon as this thing approaches us. Second one is a very interesting one. It's looking at the lunar at the solar eclipse. I'm sorry, looking at the lunar eclipse, looking at the shadow of the Earth going across the moon, right? The Earth gets in the way of the sun lighting up the moon. The shadow of the Earth moves across the face of the moon. And when you look at this shadow, it is in fact a round shadow. It's not the phases of the moon, because in fact, this shadow is the exact opposite shape. It's the exact opposite orientation that the phases go through. Okay, so there's some round object that is getting in the way between the light of the sun lighting up the moon when we go into a lunar eclipse. And lunar eclipses, right, are pretty common. You'll get a lunar eclipse once every couple of years, right? So this is also a very nice, very clever. Once you realize that it is the Earth's shadow that is creating the eclipse, well, you see a round shadow. Okay, the shape of the Earth. And the last one also is a very interesting one that some people may not realize. When you're standing on the Earth, you have a certain horizon, right? There's a certain part of the sky that you see. Okay, you see basically half the sky, the night sky. There's the North Star, and you see the North Star with respect to the horizon, and the North Star has a certain elevation above the horizon. The North Star is just so high in the sky when you stand on the Earth. Okay, if you were to move north, you would have a different horizon. The horizon would change. And the consequences of that changing horizon is that, for example, the elevation of the North Star would change. Yeah, the further you go north, the higher the North Star is for you in the sky. It's still fixed. The North Star is always fixed in the sky. It just gets higher and higher in the sky as you go north. And as you go south, the North Star gets lower and lower in the sky. I know the first time I visited Costa Rica on vacation, I went outside one night and I wanted to go look at the sky. And I looked at the sky, and one of the first things I wanted to find was the North Star. So I'm looking for the Big Dipper and looking for the North Star, and I can't find it because I'm looking where it usually is back home. I'm looking up. I'm looking up, about 43 degrees. And finally, I realized that no, you got to look. And there was the North Star right above the palm trees. It was almost at half its normal height because I was so far south that the North Star was so much lower in the sky. So the sky very much changes as we move north and south. Here is that original horizon, right? The horizon was here, and then we get this new horizon here. Look what happens. This is now visible, right? As the horizon dips down as we go north. I'm sorry, here as we let's see, we started here. Yeah, now we're here. as the horizon dips down on one side, we get stars which were not visible when we were further south. And here is the original horizon, and here's our new horizon as we go north. This now is no longer visible. Our horizon is now here. So we don't see these stars. These stars that we did see, we don't. These stars that we could see, we now see. So the sky is actually changing as we move north and south. The only reasonable explanation is that we live on a ball, and that the horizon is created by mathematically the tangent, the horizon, the flat tangent, the flat horizon that we see, the flat lake that we see, the flat plains that we see out in Nebraska. What we're looking at is the tangent line to the great sphere of the Earth. And so the only explanation for the changing sky, which was very well known to the Greeks, the Greek world went all the way down to Egypt, down the Nile, was known to them, all the way up to the Baltic Sea. So the Greek world was very much known, north and south, and this phenomenon of the changing sky was well known. And these are the three great arguments to give that the Earth was round. All educated people knew that the Earth was round. This is just a legacy slide that I have from before. Here's my little campaign, because I always want to point out the North Star, just in case, not to insult anyone, but just in case you don't know how to find the North Star. What you do is you find the Big Dipper, and you find the outside of the cup, and the outside of the cup will point to the North Star. And so that's my little campaign to make sure everybody knows how to find the North Star. So if nothing else, you could point it out to the grandkids. All right. So this round Earth is talking about grandkids. When you talk to a 4-year-old, it's very difficult for a 4-year-old, a 5-year-old with a very their literal mind, the way they literally think about things, makes them so cute in some of the things that they say. To understand that the Earth is round. If you maybe remember this yourself at some point, how do the people of Australia walk around upside down? How come they don't mind walking? Never mind, how come they don't fall off the Earth? Okay? So this idea of an absolute notion of up and down really become meaningless, right? We understand that there's a relativeness to this, that the Earth is somehow or other pulling us in towards its center, and that's what down is. Down is the direction that the Earth is pulling us at, and so we all have the same nice sense of down. So this is the first really great assault on common sense that we have in history. This is something new. This is something new in history, that we have an idea which completely violates our notion of common sense, right? Until this, we have a flat Earth. One of the reasons why we have a flat Earth is because we all want to be standing upright, and we need a flat Earth to stand upright. No, you don't. In fact, you don't need a flat Earth to stand upright. All you need is somehow or other the Earth to pull you towards its center, and you will experience a flat Earth. If the Earth is big enough, you'll experience just what we experience now, even though the Earth is round. So really a great intellectual milestone in history, to be comfortable, to understand why the round Earth can be, something that we can understand. And just while we're on the topic of assaults to common sense, what the Pythagoreans give us, they give us another assault on common sense. The first one's a physical one, the physical round Earth, and how we can make sense of that, how we can explain that to our 4-year-old. And here's a mathematical assault on common sense. You take a line, you want to measure a line. We have rulers. We use rulers to measure a line. So here we have this red line, and we want to measure it. Okay, so I have this ruler down below where I have markings 1, 2, 3, and it doesn't quite measure. It's a bit bigger than 2, but it's not quite bigger than 3. So I don't have an accurate measure yet of my red line. Not to worry, let's just put some hash marks in. Let's cut the line in by halves. So instead of having just 1, 2, 3, we'll have a half, then 1, and 1.5, and 2, 2.5, and 3. And I have more hash marks. Well, that quite doesn't do it either, right? Because it's a bit bigger than 2.5, but again, it's not as big as 3. Not to worry. You've got plenty of numbers. Let's divide the line into thirds. Getting closer. That 8/3 looks better, but still, that line is longer than 8/3. Finally, we get to fourths. Let's divide up the line into fourths: 1/4, 2/4, 3/4, 5/4, 6/4. Right? Let's break this up finally into fourths. And yeah, I think we've done it. I think here, when we break up the line into fourths, we've measured accurately this line. And the Greeks thought that you could do this for any line. No matter how long a line you draw, you can always create the finest hash marks that you need, where finally your line will touch exactly one of the hash marks. If fourths don't do it, we'll try fifths. How about tenths? How about twelfths? How about hundredths? How about breaking the line up into thousandths? Okay, you can break this up into as fine a mesh as you like. At some point, your line, no matter how you've derived it, no matter where you drew it from, will finally touch exactly one hash mark, and that'll be the measurement of that line. That would be what common sense would dictate, right? Well, there's a problem. We have the Pythagorean theorem. Okay, the Pythagorean theorem tells us if you take a simple square, how simple can you get? A square 1 by 1, and you draw the diagonal d. Well, we're told that the diagonal squared is equal to the sides, sum of the sides squared. So this diagonal, this very innocent line, how simple can you get the diagonal of a unit square? My goodness, perfectly nice line. That squared is equal to 1 squared plus 1 squared, which is 2. So the diagonal has a length of radical 2, right? And the Pythagoreans were able to show that radical 2 is not a fraction. Okay? It is a rational number. We don't have time to go through the proof, but they were able to show that radical 2 was not, in fact, a number like all the other numbers. It was qualitatively different. One way to express it is an infinite repeating decimal with no infinite pattern, no repeating patterns to it. Okay? So if you take this very, very simple line, just drop it down, okay, drop it down onto our number line, take this very nice length, radical 2. Well, what about the hash mark? Well, clearly it's bigger than 1, but it's smaller than 1.5. It falls between 1 and 1.5. Okay, well, let's start doing our thing. Let's do the thirds and a fourths and a fifths, and let's keep just making hash marks over and over again. And what the Pythagoreans were able to prove is that no matter how fine a hash marks you use, you will never hit exactly that line. The end of that line will never be exactly on any one of those hash marks. Any one of them, no matter how fine a hash mark you use. You could divide this up into tenths, or 100ths, or 1,000ths, or 1 Googles. It doesn't matter how fine you make this, that line will not end at any one of those hash marks. Okay? This is truly an assault of common sense, and the Pythagoreans were able to prove this using this very, very simple line, the diagonal of a unit square. So these are two great, really, landmarks in intellectual history that we have confronted here: the round earth and the fact that it can make sense, and numbers which are not fractions, basically, numbers which are not ratios of whole numbers. And this was a great crisis to the Pythagoreans because they built their whole mathematics, their whole universe on the mathematics of whole numbers. And here was a length, a perfectly simple length, a perfectly easily constructed length, which was not constructed from whole numbers. And this is why historians of mathematics say that the Greeks shied away from algebra. They shied away from just using numbers because they knew the number system was somehow or other incomplete because of these numbers lurking around, these very, very simple numbers that were clearly in their universe. So they shrunk away and were much more comfortable working in geometry because the line itself could be drawn. You could make a square and draw a diagonal. The line was real, and they could deal with geometric figures. How to make it into a number, they didn't know what to do with this number that because we now can write as an infinite decimal. So they shied away from manipulating with these numbers, shied away from the developing algebra, and in the process, we got a very, very powerful geometry from the Greeks, which we'll use very much as we move into our astronomical models. But they shrunk away from developing a number system because of this discovery of theirs. Okay, so the Pythagoreans contributed a lot to us. Let's go back to our story, though. Another thinker we have is Anaxagoras. He's actually the first philosopher who comes to Athens. He was a friend of Pericles. Pericles, of course, was the ruler of Athens at this time. See his dates. And Pericles invited him to Athens, and this is the first philosopher that kind of moves to Athens, and Athens, becomes the center of philosophy, as we know, with Plato and Aristotle. Anaxagoras is the one that we contribute in history who finally makes it very clear, understood, not doubted after this, that the moon is lit by the light of the sun. Okay? It's kind of obvious when you see it now, but this was a great debated point. Did the moon create its own light or what? And you can see here that these two pictures kind of try to depict that, looking at sunset as the moon is going down. The sun just went down, and now the crescent moon is going down. Clearly, the moon is being lit. And also here we have dawn. The moon comes up. The waxing moon comes up. I'm sorry, the waning moon comes up, and very soon after that, the sun will come up in the east. And clearly, again, how is the moon lit? It's lit in the direction of where the sun is. But Anaxagoras is the one who finally teaches this and is accepted by this, that the moon shines by the light of the sun, and therefore the phases of the moon are created by how much of the moon is lit, how much of the moon that we see is being lit by the sun. He also taught that the moon had mountains and valleys, just like the Earth, that the moon was not somehow or other fundamentally different than the Earth. A very modern idea. He also is the first one to explain what a solar eclipse was, okay, to take away the great fear. What is this most dramatic phenomenon in the sky? There's no doubt about it that today, in 2022, there's nothing more dramatic that we can see in the sky with our naked eye than a solar eclipse. If you've ever experienced it, you know it is. I experienced one in London back in the 80s. It was a full, total solar eclipse, and luckily went through London, and it was really eerie to just have the darkness come over and the stars come out, and then to come back again. It's an awe-inspiring sight, it really is. And Anaxagoras is the one who explained it. Nothing to be afraid of. It's simply the moon getting in the way of the sun. That's all it is. All you're looking at there is the moon as it goes around the Earth. Sometimes it just gets in the way of the sun, and it will pass by and go on its merry way. So these are the contributions of Anaxagoras. He also attempted to give other natural explanations of things like rainbows and shooting stars and things like this. Again, we're far away now, from the explaining things with gods and goddesses. We're in the tradition of natural philosophy, natural science, eventually, as we understand it. And before we get to Plato, we have to just make one slide about the atomists, Leucippus, and most importantly, Democritus. These are the people who taught that the world was made of these tiny, uncuttable atoms. That's where atom comes from in Greek. They are uncuttable. They're the fundamental substances of the universe, and everything is made of these atoms. They're all made. The atoms all are made of the same substance, whatever that is. They're different because they have different shapes, and they have different kinds of motions. And the different motions and the different shapes allow them to combine in different ways to create all the different elements that we see. But they're all fundamentally made of these uncuttable atoms. And that's what creates the great diversity that we see in the natural world. Their ideas were very, very modern in a sense. They did not have a clockwork universe. They didn't have a world which everything was determined, because these atoms, which they created phenomenon that we see. They create the world as we know it by their motion, and sometimes these motions can just move in a random kind of way. They can swerve, as the word got translated into English from the Greek and from the Latin, that they would just swerve out of their normal paths from time to time, and this would create new phenomena. This would create unpredictable phenomena, so that the universe was not this predictable clockwork of Newton came to see for a time, where everything followed these mathematical laws religiously without any change. No, no, there was wiggle room in Adam's world back then. But they did held this very, very un-Greek idea that the universe was this lifeless machine, that all it was these atoms in motion. That's what created the universe, including us, was these just atoms, and there was no grand design to the universe. There was no cosmos in that sense to the atoms. This is a very, very radical idea. And just a quote from their writings. There are an infinite number of universes of different sizes. There are some where there is no sun, moon. There are some where the sun and moon are larger than our sun and moon. Some are growing, some are at their peak, and some are declining. Here's one that's coming into being, and one which is ceasing to be. I don't know, is this the multiverse of modern physics? This is a vision of the universe which is way beyond. There's nothing like this. Never mind in the ancient world. There's nothing like this in the medieval world. There's nothing like this until we get, again, the beginnings of speculation, maybe in the scientific revolution, very tentative kind of speculations about, but nothing bold like this. You really need to move into modern science before you get this vision again. Okay. So the Greek thinkers were incredible speculators. They thought about things in all kinds of creative ways. Almost any view you can think of about the universe, there's some Greek philosopher who held that view. They had an incredible spectrum of views and ideas and imagination. They brought speculation into the Western world like never understood, never seen before. And the atomists are just a startling example of that kind of speculation. And finally, let's finish up talking about Plato, because he will set the stage for us. With Plato, we will begin to now move into our geometric models. Plato, of course, is considered the greatest philosopher of the ancient world, a student of Socrates, teacher of Aristotle, greatly influenced by the Pythagoreans. He is a Pythagorean in his training, in his temperament, and his basic idea of the universe. He is the most influential of all the Pythagoreans by far, one of the most influential thinkers in history. And what we need to review and remember about the thinking of Plato for our story is that Plato saw the world as two different spheres of reality. One was this perfect world, or what he called the world of forms or ideals. And the other was the world of the senses that we see and touch. And there were two very distinct worlds, and one was more real than the other. The world of forms and ideals was the truly real world. And our world was some kind of an imitation of that world. And if you wanted to get a glimpse of the real world, the best place to see the real world was through mathematics, because the objects of mathematics were part of the world of forms and ideals. Okay? The circle of mathematics is a mathematical idea. Okay? The definition of a circle is the set of points all equidistant from some central point. There is no such thing in the real world. You can't draw that thing in the real world. Oh, you can draw an imitation of a circle. You can draw a line that goes around a point. okay? But every engineer will tell you that there's no way that every single point on that line is exactly the same distance on the circumference from that central point. There's no way physically to even measure to do that. But as an idea, it's a perfectly clear idea, okay? That's the idea, that's the real circle. And Euclid can come along and prove hundreds of theorems about that object, although it is not real. There's nothing in the world that is exactly that object, although we can prove hundreds of theorems about its properties. This is the world that Plato is trying to describe. This is the world that Plato is telling us about. It's the world of our mind, and that's what's truly real. And what we have in the so-called real world, this world of senses, is merely an imitation of that world. You can see it's a very, very Pythagorean kind of idea. This is among the many, many ideas that Plato gives us in Plato's philosophy. This is the one that we want to take away. Okay? This will be important for us going forward in terms of his thoughts about the universe. Nice example that he gives, the famous one of the allegory of the curve, the cave, right, which we all know from Philosophy 101. He gives the story that it's like the real world is like we're like prisoners that are in a cave, and we're forced to only look at shadows on the wall. There's a fire behind us. We don't know about the fire. And between the fire and us are the real objects that are moving back and forth, and the world of ideas is happening. But the fire is casting the shadow on the wall, and all we see are the shadows. But that's all we see, so we think it's real. It's the only reality that we can actually perceive, but it's not. Okay? If we knew the full story, if we understood the world of ideals, if we understood the world of forms, we would know that what we're seeing is only imitations of what's real, and that's behind us that we can't see. So it's a fantastic allegory, one of the most famous in the history of Western thought. So we come to his cosmology, which is what is important to us. This is all laid down in one of his great dialogues called the Timaeus. This is actually not much of a dialogue. This is more of him just kind of writing and laying things out. This is the least dialogue-y of all of his dialogues. It's a fascinating document to read. And if you are interested in just wild, beautiful writing of what the universe is like, excerpts from the Timaeus is a fascinating document. But distilling what we need to know from it is that the world below the orbit of the moon is composed of these combinations of the basic four elements, earth, air, fire, and water. He is a great believer in the earth, air, fire, and water as the elements of our substances. The cosmos at the orbit of the moon and beyond is made of perfect world. This is the world of perfect forms. Not only is mathematics in the world of perfect forms, but actually the heavens is part of this perfect world. Yeah, he actually thought of the stars and the planets and the sun and moon as not having the same substance as earth, air, fire, and water. It was part of the perfect world, even though we could see it. It was the one part of the perfect world that we actually could see, and that was the heavens. The earth is a sphere, unmoved at the center of the universe, and once Plato said that, that was the end of the story until we get to Copernicus. Nobody doubted this, nobody questioned this, nobody tried to put forth anything seriously, or one very important person did, as we'll see, but it was not accepted. Once Plato laid this down, that was it. The earth is a sphere, unmoved at the center of the universe. All heavenly bodies move about the earth in perfect circular motions or combinations of those motions. And all those circular motions must be at constant speeds. Well, this is the perfect world, guys. This is the world of ideals. Of course, what is the most perfect shape? The most perfect shape is a circle. Most perfect three-dimensional shape is a sphere. So, of course, the perfect world of the sun and the moon and the stars and the celestial sphere all have to be spheres. They have to take on the perfection. And what is the perfect motion? The perfect motion is constant motion. You don't hurry the gods. You don't hurry what is divine. You don't hurry what is perfect. You don't slow it down. You don't speed it up. It moves at a constant speed forever in these infinite cycles that never change. That's the perfect world. So that's how the world must be. The planets must move in constant motions, or at least combinations of constant motions. He did give us that. I think the astronomer said, Plato, constant motions all by itself, that's not going to cut it. You better give us more wiggle room than just pure constant motions. Let me tell you, the planets do not move in constant motions. Okay, so there's constant motions and combinations of constant motions. You have to stay with that, and so they did. And so this is the cosmology of Plato, and basically this is what stays through the ancient world and through the Middle Ages and through the world of the Islamic astronomers. This basic world, as modified as we'll see by Aristotle. What Plato does in the academy, he has all of his young students here, all the brilliant minds of Greece. All the noble families bring their sons to be taught by Plato. He charges the mathematicians and the astronomers to build a mathematical model of the universe. So this is what we need. We need you to build a mathematical model of what the sky looks like in the day and the night, okay? Based upon mathematical principles. The key idea of this model is to be accurate, as to tell me exactly where Mars is. 5 months from now at 2 o'clock in the morning, where will Mars be in the sky? That's what I want this model to tell me. Okay? That's what it needs to strive to do. I don't really care about the physicalness underneath it. I don't care what you're using to make. I want just a mathematical model. Whatever devices you use, the computation should come out correct to describe. I want basically stellarium. That's right. I want you to build me stellarium, so that I can open up my model on any day, any time, in the future, in the past, and it'll show me what the sky looks like where I am. That's what I want you to build. And you need to stay within the precepts of our cosmology, okay? That these motions are all uniform and perfect circles. He summed it up by saying, I want you to save the appearances, okay? I don't necessarily want you to create what's real. We'll never know what's real. In fact, we know that what's up there is divine. It's this world of ideals. It's this world of forms. It's not even real in the sense of that we understand real of earth, air, fire, and water. So there's no point in even trying to understand what's actually happening up there. The mathematical description is all we need. We need the pure world of mathematics to describe the pure world of the stars. That is sufficient. That would be the beautiful harmony. We don't need to understand how it actually gets to be where it is. We don't need that physicalness of the model. And so this is what Plato lays down as to be done by the mathematicians and students and philosophers and astronomers of the world. And this is what is done because he's Plato. So Plato gives us what's called the two-sphere model of the universe. Okay? This is the fundamental model that will stay with us until Copernicus, that the Earth is a sphere in the center. And from Anaximenes, we have the sphere of the fixed stars around us. And the sphere of the fixed stars turns every day, 23 hours and 56 minutes. If you go, guys, here on the right, see the right shoulder, this right shoulder is coming at us, right? It's turning so that this right shoulder here is coming at us, and therefore you can see that the stars would be rising in the east and setting in the west, right? You can see Asia there, the east side. And so if the stars are here, if the sphere is coming at us from this direction, then the sky would look like it will be rising in the east and setting in the west. And this is the fundamental geometric model that Plato wants us to use. And this is what will be used for 2,000 years. Somehow or other, these 7 planets, and they talked about them as 7 planets, sun and moon, those are 2, and the 5 planets that we call planets, Mercury, Venus, Mars, Jupiter, and Saturn, the visible planets to the naked eye. It's the only planets that they knew. And Uranus is not discovered until the 1700s. So these 7 planets are somehow or other attached in some loose way to this outer sphere of the fixed stars. And as the outer sphere is turning, it somehow or other turns those as well to see what we see in the sky, to see the phenomenon of the night sky. And Plato wants the mathematicians to build a model to predict that sky at any time. He wants us to build a stellarium. And like I say, it is primarily a mathematical universe. The 7 planets can be configured in any independent way. They don't have to depend upon each other. They have to depend in some loose way about the outer sphere. The outer sphere should in some way be driving this, because the planets are going around this once a day. And besides their, big motions, the true motions going through the stars, they are being spun around, whether they like it or not, every day by the fixed stars. So they're fixed in some way. They're hanging on them gears, something or other, that's determining that motion. But you can take each individual planet and develop it independently, because we know the motions are very crazy. So you don't really have to worry. Just make each one accurate to where is Jupiter, at any time. And this is the and finally, we'll end here. Plato, in terms of the real world, going back to the real of substances, even that he makes mathematical. Okay, we have the earth, air, fire, and water. These are each of the one of the great called Platonic solids. These beautiful solids, which every single face is a equilateral figure. Most of them you can see are equilateral triangles. Here's fire as the tetrahedron, and air, earth here is a square. Here's another equilateral triangle for water, kind of the most roundness. And the universe is a separate, right? This is a perfect element. Okay, the universe has this shape to it, and they come, like I say, from the perfect, what we now call the Platonic solids of geometry. So again, this Pythagorean idea, Plato very much buys into this, that the substances of the universe are built upon these beautiful symmetric mathematical objects. And he even goes further. He gets kind of a proton neutron thing going here. He says, well, even when you look at the building of those figures, they're from even more fundamental figures. You've got the 2 isosceles right triangles will give you the square. The equilateral triangle will build the fire and the air, and the water will be built out of faces of the equilateral triangle. And finally, the pentagon, coming from these fundamental isosceles triangles, we can get the isochahedron, and so we can get the universe from there. So yes, Plato was very much Pythagorean. Plato is not a mathematician himself, but Plato had tremendous influence on the mathematicians of his day. And remember, the mathematicians and the astronomers were basically the same people. Remember, in Republic and in the Laws, his great dialogues about how to lay out a perfect world and perfect rulers who would build a perfect world. The curriculum, the first curriculum that the young rulers were given, what they first studied, was number theory, geometry, and astronomy. That's where their education began, and only after that did you go into things like rhetoric and logic and politics and things like that. Your fundamental education was one of mathematics. Okay, we'll stop there. I wanted to start the next presentation, but okay, it gives me a week off. I don't have to. Actually, it's a short presentation, so hopefully we'll finish it and go on. So I will give you a presentation next Tuesday. All right. Any questions? I know I've given you a lot of information. Questions, comments, thoughts?
I'm puzzled by Plato's insistence that the objects moved at a constant speed. And
that's because these are perfect objects, perfect forms, and the perfect shape is a circle or a sphere, and the perfect motion is constant motion. You don't slow these things down. You don't speed them up. This would be very inappropriate. This would be very unform-like, very unperfect-like. Perfect things move at a constant speed, unchanging in these endless cycles. It's just the way it is. Has
But I
to be
mean,
this
if
way.
you've got a sphere moving in a 1 mile circle and a sphere moving in a 10 mile circle, it seems that you would observe them moving at different speeds.
You know, they can move at different speeds as long as they're both constant. That's
Okay,
fine.
okay, I see what you mean.
Oh, yeah.
I was misinterpreting constant to mean.
Oh, yeah, no, not all the same speed. Okay, good,
Gotcha.
good point. Good, Mike. Very good point. Thank you. No, I should have clarified that. They all are moving at a constant speed of their own.
Gotcha.
As a matter of fact, he actually did give more wiggle room. As he said, either constant speeds or combinations of constant. And we'll see exactly how the mathematicians pick that up and begin to develop the beautiful geometry that I want to show you. Any other thoughts or comments? Okay, then we'll call it a day, and we have our next presentation all ready to go. It's a relatively short one, and I think we would be able to maybe move into the next presentation through tomorrow, through next time. So I will stop the recording.